We talked about double replacement reactions last time, where you had two ions that reacted to form a precipitate. For example, we said, and this you would have found in your packet if you worked through those problems I recommended. But when we talked about precipitation, we said that you can have two ions that react to form a precipitate. For example, if we had sodium, you don't need to write this, sodium sulfate reacting with lead 2 nitrate. This is one of the examples we had looked at previously. We said up sodium's group 1, nitrate's always soluble, and your net ionic equation will be sulfate ion plus lead 2 ion generates lead 2 sulfate. Now in this class, sometimes you generate certain products that then react further in that they may decompose. And that's what we want to look at very, very briefly here. And some of these reactions occur in your kitchen, some of them occur in your stomach, etc. So one of the things you can look at is magnesium hydroxide reacting with acid. Magnesium hydroxide is weakly soluble. It reacts with stomach acid. Inside your stomach is hydrochloric acid, so it reacts with proton to generate magnesium ion and water. And so you're generating a salt essentially that will help neutralize the acid in your stomach because it won't be that acidic or basic. Another example is with baking, and many of you have played with vinegar and baking soda and you know it bubbles up, you're generating carbon dioxide. Well, the first substance that's actually generated is carbonic acid, but carbonic acid decomposes rapidly to water and carbon dioxide gas, and that's the bubbling that you see.
What is A?
A could be any acid.
Oh, it's just a...
Yeah, just a generic notation.
Okay.
Some gases are formed in these double replacement or metathesis type of reactions, and that's what I want to point out to you, because it looks like a precipitation reaction, but instead you generate a gas. So for example, if you have hydrochloric acid and sodium sulfide, again, you would recognize the sodium ion is going to be the one that's going to cancel. Chloride ion cancels. This is aqueous, and you generate a gas. So instead of a precipitate, you generate a gas. You would recognize it in the sense that when you generate a gas, you will see bubbling. Similarly, you can generate hydrogen cyanide gas that can be very deadly. That's another gas you can generate. What I wanted to show you is here, and this will correspond with a couple of your classwork problems that we'll take a look with. Acids can react with bicarbonates, carbonates, sulfites, and bisulfites to generate gases that also you're going to generate the gas due to the decomp of this substance. So for example, this is actually a lab that some of you ran last year. You may or may not recognize it in regard to a stoichiometry lab. But you can see here that the sodium and the chloride will cancel and you generate carbonic acid. If you ever generate this substance, it will decompose to water and CO2. The same way if you ever generate sulfurous acid, it will decompose to water and sulfur dioxide. The other one that's very tricky is this one, because if you looked at this, it would be very tricky for you to figure out what canceled. Most of you would go after the sodium ion to cancel, which is good. But you also know that ammonium-containing compounds are water-soluble. But be careful, because if the ammonium ion hooks up with a hydroxide ion, you get ammonium hydroxide, and that essentially is ammonia and water. So that is very tricky. Let me show you on your classwork where to recognize these problems. We're not going to make a big deal out of it because it's going to be very simple for you. It's going to be a grossly obvious one. You had already completed the equivalent of page 3. This would be the first sheet I gave you or should have completed. I just want to do a couple of these. The gas rules, etc., that I just mentioned are here. And let's take a look at a few net ionic balance equations that we can look at here. So this is my page 5 or 51. This was not handed out today, but last time. Let's take a look at the first example to show you how to recognize this. It says ammonium sulfate and potassium hydroxide are mixed together. So this is either what I listed as page 5. Unfortunately, it didn't translate that well, or it says 51 on it. And it says ammonium sulfate and potassium hydroxide are mixed. And again, it may not be obvious what to go for. Very often with the ammonium, you dump it. But if you see ammonium ion here and hydroxide ion here, you are making ammonium hydroxide. Ammonium hydroxide rapidly decomposes to ammonia and what? Water. And so all you're going after here is ammonium ion and hydroxide ion. And they usually come out balanced from the get-go, which is nice. I'll do a few. Let's look at 5. It says potassium sulfite reacts with hydrobromic acid. Now, in just looking at that, what do you guess you're going to cancel? Potassium and bromide. So you're going to have sulfite ion reacting with proton, and at first glance you're going to say, ooh, sulfurous acid. But what does sulfurous acid break up into?
Sulfur dioxide and water.
Water and sulfur dioxide is correct. So when you generate this or you generate this, just recognize what they actually break up to. Let me find one more for you to try. Let's say, oh, this one's a mess. Let's try this one. 10 says strontium hydroxide and ammonium sulfide. And this one would not be something you were given because it's too difficult. But in looking at this, what product do you see that we generated just a few minutes ago?
Ammonium hydroxide.
There you go. So you can see this piece. The other piece is soluble. You would have to be told that, which is why we don't see that much of this anymore. This decomposes to what? Oh my gosh, I didn't realize. I'm sorry. But I'm not very concerned in regard to this. And we'll pick up with this next time.